Permutations of the word math. So the word permutations means you take whatever objects you have, in this case they're letters, and you rearrange them. And if you have four things that are all different and you're rearranging them, it would just be 4 factorial. You need this notes package? Yeah. Now, this example with putting students into desks, we have 5 people coming for math help and there's 12 desks. For whatever reason, this becomes harder because when we have spaces and we put numbers into spaces, we somehow in our brains transfer that over into desks, and desks are things that we put people into. So people are very tempted in this one to make 12 spaces. And if you make 12 spaces and you go, okay, there's 5 people, and then all of a sudden you're like, I'm going to run out of numbers to fill those spaces if I go 5, 4, 3, 2, 1. And in fact, the desks are not your decisions. What your decisions are is the first person comes in. They look around. How many choices of desks do they have? 12. The second person comes in. How many choices do they have? Well, 11 now, because it gets very awkward if you come in for math help and sit on someone's lap when you come in. So yes, you only have 11 choices, and then the third person, fourth and fifth, 10, 9, 8. So this can be summarized as 12p5 because we're starting with the number 12 and there's 5 spaces, so we could figure that out. Now, if everyone was here, if we count all the desks, 2, 4, 6, 8, 10, 12, 24, 26, 28, 30, 32, 33 desks, right? If you type that into your calculator, it is a huge number as far as the number of seating plans we could arrange for this class if we used all the desks, right? Even if we didn't, if we just did the 12 desks that you guys are in and did 12 factorial, that's still a huge number for the number of seating plans. So yeah, that's this one, 33 P12. Now, what I'd like you to do, just so that it matches with our textbook, and I like the name the textbook has better. Permutations with identical objects. How many permutations are there of the word egg? Well, we've seen this before. Normally it would be 3 factorial with 3 different letters, but because we have the identical g's, we would divide by 2 factorial. And for b, normally 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factorial, but we have 3 s's, so we divide by 3 factorial, 2 p's, 2 i's, and since there's 1 a and 1 e, we don't have to worry about those, but that would be the total number permutations of Assisipi. So when we have identical objects, there are permutations that are the same, because when you rearrange this, if I switch the s's, it actually doesn't change the word. And so we divide to counteract those identical objects being counted more than once. So there's a new street being built. You could choose one of 3 types of houses. If you go down new developments, it sort of seems like this is the case. You have a lot of houses that kind of look the same. She sold 3 of Model A, 4 of Model B, and 2 of Model C. How many ways can houses be arranged? So we can imagine this as a word. And again, there's 9 houses. Normally it would be 9 factorial if they're all different. But we have identical objects. So we need to divide out that repetition. John lives 3 blocks north and 6 blocks east of school. So we've done one like this already before too. So his house is here, school is there. How many different ways can he walk home? Wow. Well, the way that we've done this, if he's walking home, he has to go north 3 times and east 6 times. And so, as an identical objects question, that would be the number of routes. Now, we've also practiced saying and counting the routes as we go. So there'd be 1 here, 1 here, 1 here, and all of these would be 1, because the only pathway, if he wanted to get there, the only pathway he could go is straight there. I mean, there's other paths, but they backtrack. So if you start counting backtracking paths, there's an infinite amount of ways that he could go from the school to home, right? Because if you backtrack, he could go here and then go around this block 8 million times, and then finally realize that's not helping, and then go home, right? But that wouldn't be a very smart choice. And usually when you're walking home, you don't get lost. Hopefully by now that's the case. So if there's 1 to each of those routes, then we learned that we could add up the corners. This will be 2. 1 plus 2 is 3. 1 plus 3 is 4. 3. 1 plus 3 is 4. 5, 6, 7. 3 plus 3 is 6. 10, 15, 21, 28, 10, 20, 35, 56, and 28 and 56 makes 84. And if you type this into your calculator, you would have found that that was 84 as well. This is a new strategy that has not come up in our notes so far. And it's called the grouping strategy. You can take this out and just remember grouping. It's how we're going to refer to this one. So the idea with this strategy is sometimes certain objects need to be grouped together. And maybe if you're organizing something at home, right? See, what are things that you would have in your room that you might organize? Maybe you have books. And maybe you organize your books by the type of book that they are. Maybe you have video games. And you have like maybe you have different video gaming systems. So you have all your PS4 games here. You have all your Wii games here. Depending on how many gaming systems you have, you might organize them by types. And you might organize by, maybe you're like, oh, I need them from different things or different sizes, so my books go from smallest to biggest. Or I like to color code them based on their covers, or different things like that. So when things get grouped together, we follow the following strategy. We say, how many groups do we have? Factorial, and then we look and arrange in each group. So we'll start with an example to see this better. Okay? So here I have a collection of math books. Surprise, surprise. And I'm wanting to put them on my shelf, but I have 4 different calculus books, 5 different algebra books, and 4 different geometry books. And I want to keep the subjects together. So I want all my calculus books together, all my geometry books together, all my algebra books together. So first of all, I'm going to decide how I'm going to rearrange. Am I going to put my calculus books first, then algebra, then geometry? or algebra, then calculus and geometry. So I do that by writing 3 factorial. That is my number of groups: calculus, algebra, and geometry. And that makes sense because if you were rearranging C, A, and G, that would be 3 factorial. That would be the number of permutations. Once I decide, as my first decision, I want calculus first, then algebra, then geometry, then I need to go and say, well, if I do that, how many ways could I rearrange my calculus books? Well, I have 4 of them. So the next decision I need to make is how many ways I'm going to rearrange those calculus books. 4 factorial. After that, I have another decision, my algebra books. They can be arranged in 5 factorial ways. And finally, my geometry books can be arranged in 4 factorial ways. So the grouping strategy is a bit of the spaces strategy combined with permutations. Because we have a number of decisions to make, my first decision is how I'm going to arrange the groups. Which group is first, which group is second, which group is third. So we always do number of groups factorial first. Then within each group we have to say, that's another decision, once I get to my calculus books, how many ways can I arrange them? And then how many ways can I arrange my algebra books? And so because it's the decisions one, whatever answers we get here, we multiply them all together. So we use the grouping strategy anytime you want to have certain things together. And one of the questions we ran into while you guys were working up on the whiteboards yesterday was a grouping strategy one, but I hadn't taught you grouping yet. Some of you came up with different ways of counting it, which was great, but now you're going to be able to see how you could count it using the grouping strategy. So here's our next example. We got 5 people, Amy, Bill, Jill, Lee, and Tom, are sitting on a park bench. And it's springtime, and Jill and Bill want to sit together. So it's a grouping strategy because now we want to group Jill and Bill together. We still have Lee, Tom, and Amy. And so if we deal with this as a grouping question, the first question we have to ask is how many groups are there? And the number one mistake in this one is to say 2 groups, because you got Jill and Bill and the rest. But do Jill and Bill, can they sit in between Lee and Tom? Could they sit in between Tom and Amy? Yes. The Lee, Tom, and Amy don't have to sit as a group. They can be split up. So what ends up happening is we have, as our number of groups, 4 of them, because Lee, Tom, and Amy are all individuals. And sometimes this question's easier to think of as, Jill and Bill are always together. You can just think of them now as one person. And so now this is like, instead of arranging 4 groups, it's like arranging 4 people. There's Lee, Tom, Amy, and the Jill Bill, which are never apart. You might know couples like that in the school that you never see them apart after they start dating. Okay? So sometimes you create names. Like I knew someone in high school that they were never apart, and we just combined their names and just called them the Carrick, because it was Carrie and Derek and they were never apart. So that we just said, oh, there goes the Carrick. But, so here we got the Jill, Bill, Lee, Tom, and Amy. Then within the groups, how many ways could you rearrange Jill and Bill? Well, they could hold left hand, right hand, or right hand, left hand. So there would be 2 factorial ways of rearranging them. And the other ones, you can make spaces for them, but it really doesn't matter. You wouldn't have to do this, because Lee, Tom, and Amy can't be rearranged anymore. And this allows us to count 4 factorial times 2 factorial, 48 ways relatively quickly, whereas all of the different scenarios you were trying to figure out in last class take a little bit longer. The most common way of solving this that I saw people do, one similar to this, I think it was Edna and Amanda were sitting together, right? People put 5 spaces and put Edna and Amanda here and said one of the 2 could sit there, 1 could sit there, then 3, 2, 1, and I get 12 ways. And then the next thing I tried to count was them sitting here. And there's 2 and 1, and then these don't matter. 12 ways. And the next time was here, and you got another 12. And the next time was here, and you got another 12. And you added up all those cases and got 48. That was the most common way people came up with, which works. But this grouping strategy is a lot faster because you just say, okay, there's 4 groups. I'll rearrange those, and then I look, any groups bigger than 1? Yes, just the 1 group, and there's 2 factorial. Because this works well when things are simple, but when things get more complicated, as in part B, poor Tom. Don't worry, Tom gets his revenge in part 3. Anyways, Jill and Bill now want to sit together. Lee and Amy want to sit together, and so we've got Jill and Bill together, Lee and Amy together, and Tom all by himself. Well, he's still sitting on the park bench. He's not really alone. But how many ways can we do this? Well, now our number of groups is 3 factorial. Our first group can be arranged with 2 factorial. Our second group can be arranged with 2 factorial. And you don't have to put Tom in there, but you can if you want. And so we have 24 ways here. Now, part C, something happens, you can use your imagination, and now Jill and Bill must not sit together. Okay? This is a very interesting situation because usually when something like this goes down, the 5 friends just don't go and sit on the park bench anymore. It's like, yeah, we're not. But they did. But they're just now refusing to sit together. And we're not going to worry about Lee and Amy. They can sit together or not sit together. They're kind of like, okay, not too serious yet or anything like that. But Jill and Bill must not sit together. And this is where the not strategy is the easiest thing to do. Now, a reminder of the not strategy. The not strategy says count all of the ways people can sit, subtract the bad ones, and you'll be left with the ones that you want. So all the ways is really easy to figure out because there's 5 people sitting on a bench. If there was no restrictions whatsoever, it would be 5 factorial. The bad ways we did in part A. How many ways did Jill and Bill sit together? There was 48 of them. So if there's 48 ways that they could sit together, and there's 120 ways in total, when you take the 48 out of the 120, what's left, all 72 of them, would be ways that they're not sitting together. So instead of trying to count it, and there's other ways that you could count this, right? So there was a group yesterday that came up with this strategy. They said, well, we're going to put Jill here. That means not Bill there. So there's 1 person that sits there, 3 people that are sitting there, and then it doesn't matter. 3, 2, 1, 18 ways. And then they said, well, next I'm going to put Jill here. That means this is not Bill, and this is not Bill. So there's 3 choices, then 2 choices, then 2 left. 12 ways. And then Jill here, then Jill here, then Jill there. And they counted them all separately and added them up and came up with a total. That will also give you 72. But it's a lot more calculations and a lot more writing to do. So this is a good example where the not strategy, the idea of counting all of them and subtracting the bad ones, is usually the best strategy.